Welcome back, everybody. Learning is a hobby here. I wanted to finish up the exercise set for the appendix in Chapter 8 in Spivak, which I'm going to do in this video. So we'll be done with Chapter 8 finally in the book after this. But then if you watch the summary for the appendix, we still have to get through Chapter 3 and 4 in Tau. And then I want to do chapter 5 in Tau and the appendix in the book for Spivak together, so at the same time, so that we can see the two different constructions of the real numbers done together, just to compare and contrast. So let's finish up chapter 8 here. I have my solutions to the chapter 8 appendix exercise set here. There was only 4 problems, so this will be also a short video because there's not much to do. But let's go through the problems here. If I can get this toolbar out of the way. Okay, so question 1 says, so this is a few parts to this. Part A says, for which of the following values of alpha is the function f of x equals x to the alpha uniformly continuous on the interval from 0 to infinity? Here we're including 0, but obviously you don't include infinity because infinity is not a number. And then here he gives a few values for alpha. So alpha 1/3, 1/2, 2, 3. We already know that it doesn't work for when x is 2 because we did that as an example in the actual appendix. So, but anyway, I'll go through, give you sort of the reasoning that I have here. So starting with x equals 1/3 and x equals 1/2, those are uniformly continuous on the closed bounded interval from 0 to 1. And if you think about this intuitively, the tangent lines to those curves at x values when x is in the interval from 1 to infinity get less and less steep. So, they're doing something like this, right? Which means for a fixed horizontal distance, the difference in height over that interval gets less and less. Therefore, the delta greater than 0 that works when x is 1 will work for all xy in the interval from 1 to infinity, where absolute value x minus y is less than delta. Then by the lemma in the appendix, x to the 1/3 and x to 1/2 are uniformly continuous on the entire interval from 0 to infinity. All right, as for x squared and x cubed, instead of the tangent lines getting less and less steep, they actually get more and more steep as x increases without bound on the interval from 0 to infinity. And therefore, for the same horizontal distance, the vertical distance gets larger and larger. Therefore, for particular epsilon greater than 0, the delta will need to get smaller and smaller, which means that x squared and x cubed are not uniformly continuous on the interval from 0 to infinity. Right, and that's part A. So part B, find a function f that's continuous and bounded on the interval from 0 to 1, where we're excluding 0 but including 1, but that is not uniformly continuous on that interval. Right, so we actually saw an example like this already. It was the topologist sine curve y equals sine of 1 over x. We did that as an example in the appendix itself. But I wanted to give a different example, just to give another one, because why not? So here I drew a function that would not be uniformly continuous on that interval. So here it's just so it's clear what this function is doing as you get closer to 0. So notice that the width here is a half, then the width here is a quarter, and the widths keep getting halved and halved. So this width here would be 1 over 8. So as you get closer and closer to 0, you still have these sort of like mountain shapes, but they get thinner and thinner as you get closer and closer to the origin. So that's again, you can think of like if a tangent line at a point would get steeper and steeper as you get closer and closer to 0. So this function that I have drawn here, while it's continuous and bounded on the interval from 0 to 1, including 1 but not including 0, it's not uniformly continuous on that interval. Right, so that's just another example. Part C says find a function f that's continuous and bounded on the interval from 0 to infinity. Here we're including 0 in that interval, but which is not uniformly continuous on that interval. And again, here I drew a picture of a function that, would have that property. So if you look at this function here, again, I'm using these sort of like, wedge-shaped pieces to construct this graph. So what happens here is as the intervals, all these intervals, notice, all have length 1 here, but over the first interval you only get one of these little wedges. Then over the second interval you get 2 of them. Then over the third interval you get 4 of them, then 8 of them, then 16 of them, and so on like that. And this goes on forever. So again, this is a function that is continuous over the specified interval. It's bounded over the specified interval, but it's not uniformly continuous over it. Okay, that's question 1. Question 2 also has a bunch of parts. Part A, prove that if f and g are uniformly continuous on A, then so is f plus g. These are all these parts to question 2 are relatively straightforward. Here's the proof. Let f and g be uniformly continuous on A, then for epsilon greater than 0, there's delta 1, delta 2 greater than 0, such that for x minus y in absolute value less than delta 1, and x prime minus y prime in absolute value less than delta 2, absolute value f of x minus f of y less than epsilon over 2, and g of x prime minus g of y prime in absolute value less than epsilon over 2 for x, y, x prime, y prime in A. Then choose delta to be the minimum of delta 1, delta 2. Then for x, y in A, where x minus y in absolute value less than delta, f plus g of x minus f plus g of y in absolute values is equal to absolute value f of x plus g of x minus f of y minus g of y, which I'm just rearranging things here. That's equal to absolute value f of x minus f of y plus g of x minus g of y. G of y, that's less than or equal to absolute value f of x minus f of y plus absolute value g of x minus g of y by the triangle inequality, which is less than epsilon over 2 plus epsilon over 2, which is equal to epsilon, and that proves that f plus g is uniformly continuous on the same set. All right, part B, prove that if f and g are uniformly continuous and bounded on A, then f times g is uniformly continuous on A. Again, this is relatively straightforward. Here's the proof. Let fg be uniformly continuous and bounded on A, then there exists mn greater than 0, such that for any x, y in A, absolute value f of x less than or equal to m, absolute value g of y less than or equal to n. Also for epsilon greater than 0, there's delta 1, delta 2 greater than 0, such that for any x, x prime, y, y prime in A, where absolute value x minus y less than delta 1, absolute value x prime minus y prime less than delta 2 implies absolute value f of x minus f of y less than epsilon over 2 times n plus 1, and absolute value g of x prime minus g of y prime less than epsilon over 2 times m plus 1. Choose delta to be the minimum of delta 1, delta 2. Then if x, y are in A with absolute value x minus y less than delta, then in absolute value fg of x minus fg of y is equal to in absolute value f of x g of x minus f of y g of x plus f of y g of x minus f of y g of x. This is a pretty standard trick. I've done this already a bunch of times in the book, but this sums to 0, so it doesn't change the value of anything. And then this is equal to this, and this is equal to this, just by the way we define function multiplication. All right, and by the triangle inequality, that's less than or equal to absolute value f of x minus f of y times absolute value g of x plus absolute value g of x minus g of y times absolute value of f of y. And then we know that g and f are bounded, so just, all these things are less than what I have written here. So the first term is less than n over epsilon over 2 times n plus 1, and the second term is less than m epsilon over 2 times m plus 1. If you add those together, that's less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. So that shows the proposition here. So the proposition holds. Okay, part C, show that this conclusion does not hold if one of them isn't bounded, right? So I just came up with a counter example here. Let's say that f of x is the square root of x. We know that that's we know that that's uniformly continuous on the interval from 0 to infinity by the first question. And g of x equals sine x is also uniformly continuous on the interval from 0 to infinity. Then fg of x equals square root x. I'm sorry, fg of x equals square root x sine x is not uniformly continuous on the interval from 0 to infinity, even though f and g are uniformly continuous on that interval. And this follows from the fact that if you take the derivative when x gets very large, it grows like square root x cosine x. And since square root x cosine x is unbounded, there's an infinite number of points where the slopes of the tangent lines get larger and larger and larger. So that function is not uniformly continuous. All right, part D, suppose that f is uniformly continuous on A, that g is uniformly continuous on B, and that f of x is in B for all x and A. Prove that g composed with f is uniformly continuous on A. Right, again, this is pretty straightforward. Let f and g satisfy the above hypotheses. Then for epsilon greater than 0, there's delta 1, delta 2 greater than 0, such that for any x, y, and A, absolute value x minus y less than delta 1 implies f of x minus f of y in absolute value less than delta 2. And for any x prime, y prime in B, x prime minus y prime in absolute value less than delta 2 implies g of x prime minus g of y prime in absolute value less than epsilon. Then for if you choose x minus y, take 2 points whose difference in absolute value is less than delta 1, then you know that f of x minus f of y in absolute value is less than delta 2, and that implies that absolute value g of f of x minus g of f of y is less than epsilon. Right. Okay, question 3. Here he says, use a bisection argument to give another proof of theorem 1. Right, theorem 1, here he's referring to theorem 1 in the appendix. Right, so let f be a continuous function on the closed interval from A to B. Assume for the sake of contradiction that f is not epsilon good on the closed interval from A to B, and then we'll construct the following nested sequence of closed intervals because you want to just do a bisection argument. So let I1 be the left-hand half of the interval from A to B, and let I1 prime be the right-hand half. Choose one of these intervals over which f is not epsilon good, then bisect this smaller interval into I2 and I2 prime, and you just keep going on, and choose one of those where f is not epsilon good, and you could just keep going on and on like this, right? So if we do that, we get this sequence of closed bounded intervals, I1, I2, I3, et cetera, that are all contain the next one. So by the nested interval theorem, the intersection of all those intervals is not empty. Take a point in the intersection, then f is continuous at x because we know f is continuous on the entire interval from A to B. Therefore, for epsilon greater than 0, there's a delta greater than 0 such that for absolute value y minus x less than delta, absolute value f of y minus f of x less than epsilon over 2, then if y prime are in the interval from A to B, such that absolute value y minus x less than delta, y prime minus x less than delta, then if you look at the positive difference between y and y prime less than delta, then you look at absolute value f of y minus f of y prime, that equals f of y minus f of x plus f of x minus f of y prime. Again, I'm using that same trick that I used before where I'm adding 0, right? F of x minus f of x is 0. That's less than or equal to absolute value f of x, f of y minus f of x plus f of y prime minus f of x less than epsilon over 2 plus epsilon over 2, which is epsilon. But however, this contradicts that there is one of those intervals in our sequence of nested intervals that is contained completely in the interval from x minus delta to x plus delta, such that f is not epsilon good on that interval ik. Therefore, f is epsilon good on the whole interval because of the contradiction. Okay, so that's another proof of theorem 1, but using a bisection argument. All right, last question in the exercise set for the appendix for chapter 8. Here he wants us to derive theorem 7.2 as a consequence of theorem 1. If you don't remember, theorem 7.2, here I'll bring it up, says this: if f is continuous on the closed interval from a to b, then f is bounded above on that interval. That is, there's some number n, such that f of x less than equal n for all x in the closed interval from a to b. So we want to prove that as a consequence, that follows as a consequence to theorem 1. Right, so here's my proof. Let f be continuous on the closed interval from a to b. That means f is uniformly continuous on AB by theorem 1, the one that we just proved. Then for epsilon equals 1/2, for example, there's delta greater than 0, such that for any xy in the closed interval from a to b with absolute value x minus y less than delta, absolute value f of x minus f of y less than 1/2, by the Archimedean property, we can choose n in natural numbers large enough so that delta equals, which I'm defining to be equal to b minus a over n less than delta. Since the n points a plus delta, a plus 2 delta plus dot dot dot, up to a plus n delta, which would be the n, the point b, right? That would be the upper end point of the interval. Since those points partition the interval from a to b, and xy in the interval from a to k delta a plus k delta, comma, a plus k plus 1 delta implies absolute value f of x minus f of y less than 1/2, then f of x in absolute value f of x minus f of a has to be, at most n over 2. It can't be bigger than that for any x in the interval from a to b. Therefore, I'm just using the triangle, a version of the triangle inequality here. Absolute value f of x minus absolute value f of a is less than absolute value f of x minus f of a, which is, we just saw, was less than n over 2, implies that f of x in absolute value less than absolute value f of a plus n over 2 for all x in the closed interval from a to b. Therefore, f is bounded on that interval, and that proves the theorem. And that's it. That's the exercise set for the appendix in chapter 8. So let me just stop the screen share. So that's the end of chapter 8. So now we can move on to chapter 3 and 4 in tau. We'll get through those, and then we can finally construct the real numbers. We're going to do it 2 different ways, and then finally after that we can get to the derivative and integral chapter of Spivak. So I'll see you guys then. Again, please do like and subscribe. Let me know what you think down below as well, and I'll see you guys in the next video.